So, now as I discussed I said right in the beginning that we are interested in getting the solution concept, how to solve a general extensive form game. So, for that of course, we have backward induction, but we are going to modify it little bit. What do we have? That start from the smallest subgame containing the terminal nodes of the game tree. Remember what happens when we have the smallest subgame with the terminal nodes? In most of the cases, there is no strategic interaction left. A player decides and game ends. So, their player can very easily decide. Now, of course, what will have determine the action that a rational player would choose at that action node just before the terminal node. Replace the subgame with the payoff corresponding to the terminal node that would be reached if the action were played, and repeat until there are no action left. So, this would be clear when we do it. Let us do it for this game. For example, here we know this is a subgame. Okay. So, we will do it for the here player 2 would take this game in this direction. So, this subgame can be replaced by here payoff 2, 3. Why? Because player 1 knows player 2 is rational, and given a chance player 2 is going to decides in this direction. Now, we have the whole game. How would we solve it? Okay. So, very simple, we will do the normal form of the game. We will do the normal form of the game, and I had already modified this, I had put it as 2. We can get the normal form game. And what would be the normal form game? Again, let me point out here, let us say x, let us give them name, left, center and right, and here A B A B. And we can make the table as we have already learned in one of the previous modules, that player 1 has how many action now? LCR 3. Here we do not have to worry about. So, player 1 is going to take action LCR. How many strategies player 2 has? In fact, 2 here and 2 here, 2 multiplied by 2. So, 4, but we do not have to take care of the 4, because we know if game reaches to this point, this is what player 2 is going to do. So, we will take a reduced game in which this game tree is replaced by the outcome from the smallest subgame. So, what we will do here in the reduced form, player 2 has either A or B. So, if player 1 plays L and player 2 plays A, game will reach to this. So, payoff would be 4, 1, and similarly let me write 0, 2, here 5, 1, here 1, 0, and if player 1 plays R, no matter what player 2 does, here we will have 2, 3, 2, 3. Notice we got rid of this one, and then we solve. How do we solve? Just for revision, we try to obtain the Nash equilibrium. What do we get? If player 1 believes that player 2 is going to play A, the best response of player 1 is to play C. If player 1 thinks that player 2 is going to play B, the best response is R. Okay. Now, if player, let us do it from player 2's perspective. Player 2 thinks that player 1 is going to play L, then the best response is B, and similarly we get here this and here this. So, we get 2 Nash equilibrium C, A and R, B. Notice that player 2 does not have any strategies named A or B. Player 2 has a strategy named, if we put here x and y, then player 2 has strategies named AX, BX, AY and BY. So, how can we give the equilibrium? It is very clear that player 1 equilibrium would be that player 1 plays C and player 2 plays here A, but here we know no matter player 2 is always going to play Y. So, we can say player 2 is going to play AY, and similarly here we can say what? player 1 plays R and player 2 plays B, and of course, here Y. So, B Y. These will be the two solutions that we can get, that player 1 takes a strategy C and player 2 takes a strategy A Y, or player 1 takes a strategy R and player 2 takes a strategy B Y. In fact, we did the modified backward induction. This is what we call subgame perfect equilibrium. What is subgame perfect equilibrium? First of all, to understand subgame perfect equilibrium, let us understand the continuation strategy. What do we mean by a continuation strategy? A strategy for the original game also defines a strategy for each of its subgame, sometimes called a continuation strategy. So, what we meant here, that when we have By and this particular subgame has reached, what would be the continuation strategy in this subgame? Only Y. Similarly, for Ay, the continuation strategy would be only Y. Okay. Now, a strategy profile of a sequential game is a subgame perfect equilibrium. In short, it is called SPE. In some books, it is also called SPNE. It includes a Nash equilibrium for every subgame of the original game. Okay. So, if we treat subgames of the original games as independent game, then subgame perfect equilibrium should induce Nash equilibrium not only in the whole game, but also in all the subgames. So, in other words, the strategy is perfect even if player never goes to that part of tree. And an imperfect equilibrium is like a strategy that would not be optimal if the other player did something different. Remember, we talked about the mistakes. What if player makes a mistake? In that case, if a strategy profile is subgame perfect equilibrium, no problem. But if a Nash equilibrium is not subgame perfect equilibrium, then you would not get the optimal result. Of course, by now you must have noticed that any subgame perfect equilibrium is Nash equilibrium, but not all Nash equilibrium of the game is, not all the Nash equilibrium of the game are subgame perfect equilibrium. Although wherever we can obtain result from backward induction technique, backward induction equilibrium definitely is subgame perfect equilibrium. Okay. What again, this is something I am saying, but I will revisit this statement in other module where we will talk about credibility. A Nash equilibrium that fails to be subgame perfect is also known as Nash equilibrium supported by non-credible equilibrium. So, if I want to give you the basic rule how to obtain subgame perfect equilibrium, use backward induction first. If you can use backward induction, well and good, the equilibrium that you are getting would be subgame perfect equilibrium if you are mindful of the strategies of players. Do not just write outcome as the equilibrium. Equilibrium always means the strategy profile. Equilibrium should give one strategy for all of the players involved in the strategic interaction. And if backward induction technique fails, use techniques learned from the normal form game in the remaining game, not subgame, in remaining games. Let us take an example. This example is given in Professor Martin Osborne's very famous book, An Introduction to Game Theory. What we have here, that we have player 1 can take one of these three actions, C, D or E. If player 1 takes action C, then player 2 can take action F or G, and similarly I have written if player 1 takes action D, then player 2 can take action H or I. Similarly, if player 1 takes action E, then player 2 can take action J or K. Here backward induction, the vanilla form, the earlier backward induction has a problem. Why? For player 2, it is optimal to take any one of these two action. Even if player 2 takes F or he takes G, his payoff would remain same. So, next here player 1 2 again can take either H or I. In both cases his payoff would be 1. Here it is clear that player 2 would take K not J, because K gives 3 and J gives 2. So, this is not possible, we can get rid of this right in the beginning. Mind you, how many sub games do we have in this game? One sub game starting here, the whole game, then another sub game starting here, another sub game starting here, and another sub game starting here. So, we have a total of 4 sub games. How should we proceed now? This we have already indicated. Notice that we can say the best response from player 2. What would be the best response from player 2? No matter what player 1 is doing, best response would be FHK. What is FHK? Play F if given a chance in this node, play H if given a chance in this node, play K given a chance is this node. But this is not the only best response. What are the other best response? F, I, K. What else? G, H, K and G, I, K. These are the 4 best responses from player 2. Anyway, I have written it here. These are the optimal strategies for player 2. Given this optimal strategy, what would be the optimal strategy for player 1? If let us say player 1 thinks that player 2 is going to play FHK. Okay? So, if he plays C, he gets 3. If player 1 plays D, he gets 1. If he plays E, he gets 1. So, of course, he is better off by playing C. So, C comma FHK can be an equilibrium, and it is also sub game perfect, that although the path that game would follow is going to be this, but even in this sub game this is going to follow this path which is optimal, and here this path. So, this is sub game perfect. Okay? I will give you one more sub game perfect and then request you to obtain all the sub game perfect equilibrium of this game. What? Let us say if player 2 plays G, H, K, what would happen? If player 1 plays C, then he gets 1. If player 1 plays D, then he gets 1, and if he plays E, then he gets 1. Okay? So, here we have he is indifferent between playing C, D or E. So, all are equilibrium, C, G, H, K, D, G, H, K and E, G, H, K. Okay? Here I have written all the C, F, H, K, C, G, H, K, D, G, H, K, E, G, H, K, and you can obtain all other sub game perfect equilibrium. Okay? So, I hope now by now you have learned how to figure out the sub game perfect equilibrium SPE or SPNE of an extensive form game. In the next module, we will start talking about some of the application of extensive form game. Thank you.